Hey, howdy everyone. I'm Michael Pyrcz. I'm an associate professor at the University of Texas at Austin, and I record all of my lectures and put them online so that anyone can learn, benefit, join in. I believe in open access to education. So, to all of you working professionals out there, hey, howdy. Thank you very much for tuning in, and to all my students, I hope this is helpful. So, we have been talking about machine learning for a while now. We've worked our way through talking about a variety of topics. There's always been a bit of a method to my madness from the standpoint of exploring in a stepwise fashion in a way that we introduce new concepts as we go along. So we've covered a lot of different methods. Now it might seem like backing up a bit for polynomial regression, but you'll see it allows us to talk about basis expansion to a higher dimensional space for the purpose of making predictions with more flexibility. And we'll even get a chance to talk about Hermite polynomials, which is like super awesome. So how do we motivate this? What do we think? Well, let's get some experience with using basis functions, and we'll do it in a very simple kind of tame manner. We'll talk about how if we can transform and expand our features to higher orders, that we'll gain greater flexibility. Now we're going to pay in a loss of interpretability of our coefficients of our model, and potentially, as always, the enemy at the gate is model variability. And so we've talked about that a bunch of times. Now if we're going to talk about polynomial regression, we really have to start with linear regression. We've covered this so many times that I'm fearful. We went through ridge and lasso and all that. I'm fearful if I go into too many details, there may be a mutiny and people will just leave my channel. So let's just make a couple important concepts kind of clear, remind ourselves about them. So you can run one line of code in Python and build a linear regression model, multilinear regression model if you have more than one predictor feature. Not a big deal. I'm using SciPy here to do it. You could do it in scikit-learn just as well. And so we can get our simple model here where response feature is just going to be a function of a linear weighting of the predictor feature plus some constant term. And so we're really predicting our model with a simple line. If we were dealing with one predictor feature and one response feature, but if we were dealing with, of course, multiple predictor features, now we're talking about a plane or a hyperplane if we go past two of them. So not a big deal, pretty straightforward, and fortunately many things in the world behave in simple linear manner. Not all, of course, and many times we have to go beyond, but these models are very simple and they have analytical solutions for them. We want to take advantage of that very simple linear type of weighting framework to be able to solve our problems. And so, but we want greater flexibility. So we'll rely on a basis expansion. And so what's the motivation? Once again, we'll add flexibility, capture nonlinearity in our model for regression classification. The basis expansion, to define it, is really we're going to expand the dimensionality of the problem. We're mapping into a higher dimensional space, higher than we had before with the 1 through m predictor features. By taking the original predictor features and applying a set of functions to these original features. But we're still going to use linear methods on the transform features. And so what does that look like? We would have an H transform that'll be applied to all of our available data, I equals 1 through n data, and it will have multiple orders to it. The first order, the second order, through the kth order applied to the data. And so this is pretty cool. If we have k orders we're going to apply, our original predictor features were just 1 through m. Now for each one of them, we're going to 1 through k orders that we can apply. We're expanding it. So here's what it would look like for a polynomial expansion. We could take an original predictor feature value, I, where this would be for I equals 1 through n number of sample data, and we could apply the first order transform of our polynomial expansion. Now if you look at that, you'll see it's just the identity. At the first order, we're just going to say just preserve the original predictor feature. The second order would be we're just going to go ahead and take the square of that predictor feature for that data value, and the third order, the cube, and so forth, and we'll go on and on and on. This is polynomial expansion. Quite simple, but there is something very important about it, and that is whereas the original data table was going through 1 through n samples and 1 through m predictor features, with the basis expansion, we have mapped our problem into a higher dimensional space because we now have, as we did before, 1 through n sample data, but we now have 1 through m times k orders of the basis expansion. So we have expanded the number of predictor features we're going to use in the model. We're working in a higher dimensional space, and we're using nonlinear transforms. So now with those transform predictor features, we can build a model that is not strictly linear, but we'll use linear methodologies to do that on the nonlinear transforms in this expanded data table. That's pretty cool. That's pretty powerful stuff. So if we think about now our estimation model in the case of multilinear regression, what we're going to have is we actually have two sums. Previously, we were summing just over the predictor features. Now we're in fact going to sum also over the orders of expansion. And so, as I showed in the data table on the previous slide, whereas we had 1 through m coefficients for our model plus the constant term over here, now we're going to multiply that by k because we're going to have the k orders of the expansion. And so we'll do that up to a specified order. And so you can imagine if we were to actually apply this transform, this is what it would look like, just like on the previous slide. And if we take the example of a single predictor feature, in other words, m is equal to 1, and we just try to expand this model just to make sure everybody's on the same page here, up to the fourth order of the polynomial expansion, this is what our prediction model would look like. We would simply be with one predictor feature. We'll have 4 separate terms here going from first to the fourth power, and we would have the constant term still. So we're gaining a lot of flexibility. Now, how do we solve for the coefficients of this model? Well, what's beautiful about this is that after the nonlinear transforms, we're going to treat this model like it's a linear model. We're taking a linear combination of the nonlinear transforms, which means that we're able to utilize all of the previous math we talked about. In other words, we have access to the analytical forms that were described when we discussed in greater detail and proved the solutions for linear regression. So we're assuming linear after application of our nonlinear basis transforms. Now the model coefficients are related to a transform version of the initial predictor features. That's why we say we lose interpretability. Because now before it was really simple. We'd say, okay, we got this coefficient related to porosity, and you could see directly by its magnitude and its sense, negative or positive, what would be its impact or the strength of its impact, and you standardize the variables. We were even using that for feature selection. But now you're going to have another coefficient related to the third order, the second order, the fourth order, the fifth order, and so forth. And that gets, how do you interpret the fact you have these multiple coefficients for different orders related to a specific predictor feature? So that makes it more difficult to understand. So let's just talk about the advantages and disadvantages, comparing and contrasting with linear regression. So polynomial regression versus linear regression. You got to improve flexibility to fit nonlinear phenomenon, and we're doing it with linear analysis. That's cool. But there's always a cost. And so the disadvantages include significantly higher model variance, and we'll talk more about that. If you think about it, there's going to be greater sensitivity to outliers, because now you're taking, in the case of polynomial expansion, up to a power, and I say show it as p, but it could be just shown as k as we did before. If k or p is large, then we're going to be in a situation where you could imagine if you have an outlier value and now you're taking a power of it, it becomes even more of an outlier, and the model being usually we're going to be using an L2 solution, as we've shown before, an L2 norm. The result is they'll be very sensitive to those results. We lose coefficient interpretability, and I mentioned that already because now we're dealing with multiple coefficients related to multiple basis expansions at different orders for the original features. That's much harder to interpret and understand. Now, there's an alternative interpretation of the whole polynomial regression approach, and I like this. This is the idea, because if you look at the model, for each of the predictor features, we're taking a weighted combination of these nonlinear transforms. And so if you were to work with a single predictor feature and then have k basis expansion, what we're really doing is building a model by taking those nonlinear transforms of the original feature, second order, third order, and so forth, and we're building an additive model. We're adding them together, and that's cool. We're adding basis functions. And so let's give ourselves an interesting problem. We can talk a little bit more about it. Now, this problem is highly nonlinear. I specifically used this data set with cyclicity so we could take advantage of nonlinear methods. It'd be pretty boring if I gave you a linear method to demonstrate this. We're going to predict porosity from standardized depth. So standardized porosity from standardized depth. I'll talk later about why I've standardized everything, but we're going to do it all in standardized space. Now we're going to construct a model by adding multiple polynomial basis functions together. Now over that standardized depth, these H transforms for our depth are just shown here. Now this is no surprises here. We could have a zero order, which is a constant. We have a first order, which is a linear, the blue line. It's just got a nice linear slope. We've got the second order, which is a polynomial of second order, which would be a parabola. And we've got the third order in red. You can see it's become an odd function as we would expect. And we're back to even again with the fourth order. Much more rise on it because we got a fourth power on it. Okay, so this is what it looks like. These are the components we're going to add together. Now, you can think about it as taking each one of those and scaling them, moving them, and building a function that's just the addition of each one of them. Now, how do we do that? Well, just think about a second order. Imagine we're working with a second order. If you had a second order, which is just a parabola, if you wanted to shift it back and forth, its individual component back and forth, it's pretty straightforward. In fact, you could do the shift just by applying a subtraction of the delta x. How much do you want to shift it in the positive direction? Now, if you expand that term out, what you'll find is that you actually go from just having an x squared term to having an influence on the coefficients in the lower order terms, the constant term here and the first order term here, the x to the 1 power. So in other words, if you're shifting the function back and forth, you're going to have an impact on the lower order coefficients within the polynomial expansion. That's kind of cool. That gets kind of tucked in with what's going on with the linear component and the constant component. If you shift in y, that shift in y is just going to be in addition to the constant term. You see this? There's no x's here. So we can actually talk about shifts in x and y just being related to changes in the coefficients of the lower order terms and the constant term. That's pretty cool. So far so good. What about flipping the function? Well, that's simple. Just change the sense of the coefficient in front of the x squared term, and you can have a parabola going up or down. You can flip it upside down, and you can change the slope by changing the second order or the squared term to make it go wider and shallower or steeper. So in other words, you can think of us taking a parabola, moving around our space and trying to fit it to the data. Now, of course, simultaneously, we're going to be fitting the first order, and we'll be fitting the constant, and we'll be fitting the third order, and so forth, and changing all of their parameters, and they'll have similar influences on their own coefficients and on the lower order coefficients at the same time. And so really we are adding together multiple structures together, all based on that single number line of the predictor feature. And so here's our fourth order right here. Looks pretty good. This is a polynomial regression model. Now, if we looked at it and we checked out, I'm not going to go into detailed model checking. We've done all that before, but we could calculate the variance explained. We could show the fact that we in fact have built a model, given the constraints of the polynomial expansion of the predictor features, that has minimized the residual sum of squares or the mean squared error at each one of those locations of the data. Okay, so that's good. We've built a model. Now, just like we had before linear regression models, there's important assumptions about the data in the model. First of all, we're going to take on a lot of the assumptions of the linear regression model. We're going to say that we're error-free. The predictor features, their basis expansion, are error-free. In other words, we may have error in specifically in the data going up and down. We know there's going to be error around this model, but we're not allowed to have error on the x direction. In other words, we're assuming that the individual predictor features and their basis expansion are perfectly known. Constant variance, homoscedastic. Every time I say that, that makes me cheerful. I got to say that at least once a day. It's like eating fruits and vegetables. It is the error in the response is constant over the predictor value range. And the basis expansion of that. And so the model is homoscedastic. Linearity, we are assuming that the combination of the nonlinear transforms, basis expansions, that itself will behave in a linear manner. And it makes sense too that we're assuming that a polynomial relationship in fact exists between x and y, that it can be fit by that form. And that's pretty axiomatic. We've chosen that model. Independence of error, if we were to track the errors across all of these locations, that they would be independent of each other. There's not a systematic error with regard to the training data. And no multicollinearity. Now this is a problem with all of our models. None of the basis feature expansions are linearly redundant with each other. And so let's talk a little bit more about that and motivate the idea of Hermite polynomials for the purpose of our expansion of our original predictor features. So here's the problem. Can we say that our polynomial basis expansion in fact has a low degree of linear correlation between each of the orders? And the answer is we actually cannot. There exists a pretty high degree of correlation between our polynomial bases. There may be a high degree of correlation. Now, when we do linear regression, we're really assuming the predictor feature matrix is full rank. In other words, the columns are linearly independent of each other, and that we have, if we say we have m pieces of information, there are m pieces of information, and we don't have things as linear combinations of each other. But let's go ahead, if we go back to that model we just built, and we look at the basis expansion of the original training data set, and we calculate the correlations, a correlation matrix between the first, second, third, and fourth polynomial basis, what you're going to see is that, look at this, the third and the first, the second and the fourth, which makes sense. They're odd, even functions. With just a change in their slopes, they're actually highly correlated with each other. And this is contradicting this assumption of the model. Now, what's the result of that? Well, model instability. We talked about the issues of multicollinearity, and we don't want that to happen. Now, spoiler alert, in this problem, it's not too bad. We do okay, but in general, this could be a problem. Also, if we did not have correlation, then we could interpret each one of the coefficients as describing kind of an associated separate component of the model. And so this would be really kind of cool. When we have high degrees of correlation, it means each one of the coefficients of the model, in fact, are, kind of mixing things together. And so I know when we talked about the basis expansion of polynomial regression, we already surrendered and said interpretability is going to be low. But it's even worse when everything's all correlated with each other. Let's introduce Hermite polynomials. Now, if you look at this, there should be no surprise. In fact, up to the second order, it's almost the same as our polynomial expansion. The first order is the identity. The zeroth order is simply a constant. The second order is an x squared, but we do a -1. The third order, you can see they start to deviate as we get into higher orders. But it's kind of a same idea. The unique part is it's a family of orthogonal polynomials on the real number line. Now this is super powerful. They're in fact bases that, if we use them properly, will in fact have orthogonality. In other words, they're not going to be linear combinations of each other. They'll have a very low degree of linear correlation, and that makes them more powerful. Now, I already said we have to use them properly. And one of the things we have to realize is that it only works if they're weighted by the standard Gaussian PDF. And so let me explain that. Let's step back a little bit and we can do a little recall here. If I have two functions, f of x and g of x, over the interval a to b, they will be orthogonal to each other. These functions are orthogonal to each other if the integration from a to b of the product of these two functions is equal to 0. Now, this holds, in fact, for Hermite polynomials only under the condition that we have a weighting function which equal to this exponential right here. Now, if you look at it really carefully, this weighting function, in fact, is just the standard Gaussian probability density function. We'll remove this scalar 1 divided by square root of 2 times pi. Not a big deal. So, which means Hermite polynomials are going to be orthogonal under the condition we integrate from negative infinity to infinity of two different orders of the Hermite polynomial applied to our data set, our training data, as long as the data has this weighting function, which means it has to be standard Gaussian distributed. Okay, so and as long as, of course, the orders, we're not comparing the same order of itself. It makes sense. That would be perfectly correlated. Okay, so it has to be standard normal probability distribution. And so this is where I step back and I say, hey, you remember where I standardized this data set? Well, what we'll do is we'll in fact do more than standardization. We'll do a Gaussian anamorphosis. So now our properties are Gaussian distributed. In other words, our predictor feature is Gaussian distributed. Not just standardized depth, but Gaussian transformed to standard normal distribution. All right, so let's just take a look at them. This is kind of fun. The Hermite polynomials over our, and I apologize, this should say Gaussian transform depth is now, these are the shapes right here. Now there should be no surprises when we talk about the zero order. Remember, it was constant. When we talk about the first order, it's just the identity once again. The second order, there was just a minor shift. But once we get up to the third order, you can see things are starting to change. We had an x cubed, but we also had a first order term in that polynomial at that point, and so forth. And you can see by the fourth order, things are getting pretty complicated. So as long as we have the right probability density, the weighting is standard normal, these should become orthogonal and have low correlation with each other. So here's an example. So what I did, built right into all of the packages in SciPy, we have methodologies to be able to do Hermite polynomial expansions. I did that all the way up from 0 to 4th order, and I built myself a really nice looking model right here. This is my model. Now, one thing I want to admit, if you pan back and forth through this lecture, you'll see there's literally almost no change. And so we're in a situation where for this problem, we had not too many issues with the degree of correlation between the basis expansion of the predictor features. It was a pretty simple problem, a low order, and so we don't see too much of an advantage of using Hermite polynomials here, but it did give us a chance to get into the topic. It's a powerful topic, and to suggest it as an alternative to polynomial expansion for the purpose of building more robust models. Now, if you're interested, all of this, as always, is available on my GitHub account with the workflow that I showed in the slides, all worked out, well documented. If you go to my GitHub account, GeoStatsGuy, you can go to the numerical Python demos. There's a lot of demos here, and right here there is the polynomial expansion. So you can go ahead, and if you like, you can open that up and take a look. That's going to take a little bit of time to load. I won't wait for it, but check it out, and you can walk through this workflow yourself. If you come up with improvements, hey, everything's open source, so co-authorship is very easy. Just help out on a workflow. Okay, so I hope this was helpful to you. I think it's a very interesting topic with some really intuitive ways to get at it. Improve flexibility, accepting some more model sensitivity, model variance. All right, so I am Michael Pyrcz. I'm an associate professor at the University of Texas at Austin. I am also the Geostats Guy on Twitter. YouTube, I have a channel, Geostats Guy Lectures, and as I just showed on GitHub, Geostats Guy there too. I hope this was helpful to you. If you have any questions, go ahead and contact me. I always like discussing with people. We all learn together. All right, take care.